In this screencast, I will demonstrate you several techniques in R that are related to multiple linear regression. If you have questions regarding the theoretical background, then recruit the slides related to the session. The first thing that you do is to set the working directory. I've already done that. So here you obviously have to adjust the working directory to your machine. In RStudio, you have a direct option to set the working directory and move to the desired directory. Otherwise, you can use the file.choose command that has been shown in previous session. I won't deal with that here. The research question that we try to answer today is which patterns and environmental variables control the diversity of marine ostracods? And this research question is not just one that has been virtually constructed by me or anything. This is a research question related to a paper. You find the article here. It has been published in the Journal of Biogeography, and the authors provide the full data in the Triad repository, so we can use this original scientific data to repeat the analysis. Although we won't repeat it exactly, we will focus on the different techniques that I explained in the lecture. So the first thing that we do is we load the data. And once we have done this, we can have a look at the data. So everything went fine during loading. We see we have several variables here, and these variables are all more or less numerically. The meaning of these variables is not discussed in detail in this course. I refer you to the paper to read about the different variables and their meaning. However, we should know that E100 is our response variable. It's the species richness verified to 100 individuals. This means if you count 100 individuals, how many species will you find in a sample? We've also several variables, that's the MDS1, MDS2, DCA1 and DCA2 variables. These are outputs of community analysis, and to predict an endpoint of the community, such as species richness, we can't use the community data itself. So the authors use these as endpoints in the article for other analysis. We won't do this here, so we remove these variables from the data set in the first place. So we remove this. This is done. You see here, this looks a little bit complicated. The crucial aspect is that you have, and this is something that you certainly know, you have squared brackets that you use for subsetting data of a data frame or also of lists and or matrices, and here we have a function that tells our which columns should be used. The crucial aspect is here this command, and this tells our that every of the names that are found in the data OC, so if we would just execute this bit, we would see this calls different columns in the data set, the names of the columns to be precise, to identify those that equal MDS1, MDS2, and so on. So if we just execute this bit, we see we obtain a vector of false and true, so a logical vector, and with the exclamation mark we produce the opposite of this vector. We reverse, we could create the inverse of this vector. So false becomes true, true becomes false. And this basically means that those information or those columns that have community information can be removed. Because if you have a column, if you have a logical vector provided for the different columns true, tells R to keep the column false means to remove that column from the data set. So we execute this and have a look at the data set again. We've called it data OC2. And we see that these columns have been removed now compared to the data OC. You can also look at the head of the data set again and see that we were successful in removing the variables. Now the question is, should we transform any of the variables before we run the multiple regression analysis? So we have a first look at the data and on the histograms. What we see here is that particularly dp, so that's for the depth, and this variable is shown here, and the variable bt, they look fairly skewed. Of course, not all of the other data show perfect normal distributions. We don't really need perfect normal distributions, but for data that has a wide range and that is very skewed, it's advantageous to transform the data before analysis. And this is particularly the case here for depth. Depth has a range from apparently a few meters to 250 meters, so spans almost 2 orders of magnitude, while BT has a relatively narrow range of data. So we transform depth, and that's actually what the authors of the original study did as well. We look at the data again and we see that now we have removed the skewness of the distribution, have a fairly normal distribution of the data. So we add this to the data set. After we have added the variable, we move on to check for co-linearity. Co-linearity means that we look for variables that exhibit a high correlation, or several variables that together are highly related. Before we do this, we remove the response variable and the non-transformed depth variable, as well as species richness, because this endpoint is the original species richness, so not the rarefied species richness, we won't use for explaining in explanation. So we remove all these variables, and we do this using the same function as before. I have explained that with searching for the names of data OC, we can remove these columns. A function that is very handy to look at bivariate relationships between explanatory variables, between predictors, is the pairs function. So here we can see the relationship between variables, and we see that for some of the variables in C we see a relatively close relationship, for example between IC and P, between IC and SP. Although these are curved relationships, we see that there is a clear pattern. The plot is not particularly nice. We can obtain a little bit nicer plot if we execute this part of the code. I won't go into details here. This basically creates paired scatter plots that have different information in the upper and lower triangle of the plot. So what we see here, we see below the relationship with a smoothing line, and we see here the hypothesis test on relationships, the correlation coefficient along with a star for statistical significance. The larger the number that is displayed means the higher the correlation. What we see is that indeed IC correlates significantly with several other variables. There's also relatively close correlation between SA and the logarithmic depth. We can also use a correlation matrix to produce this result. This basically confirms what we just saw. Just do this here for the purpose of demonstration. And we check the variance inflation factor. Later in the course we will also demonstrate how to use another technique, variable clustering, and this is done later when we discuss cluster analysis. If we want to check the variance inflation factor, and for details on this factor I refer you to the lecture slides, then we first have to fit a model with all variables. So this is basically the start model, a linear model. You've already fitted a linear model for two variables, so one explanatory and one response variable. What we do here is we create this model for multiple explanatory variables. The nice thing in R is here that we don't need to enter individually each of this variable in the formula, but we can just enter a point, and this point is a placeholder for all variables that are contained in the data set, data frame, data check. So if we execute this, we would now have a look at this object. Comes a long list. We see that there's a formula of the terms. They are displayed here. We see the E100, so the verified species richness, as explained by RC, BT, SA, SP, and so on for all the individual variables, and we don't need to bother entering that. Now we load the library car. This library can be used to calculate the variance inflation factor, and this is done with the function with bracket open, then the model object where you want to calculate the variance inflation factor for, bracket close. And we obtain here the results for this computation. What we clearly see is that IC has the highest variance inflation factor. It means that it's most explained by other variables. It has the highest R square when explained by other variables. There are rules of thumb when the variance inflation creates a problem. The rule of thumb is a factor of 4 or 5. We see that basically IC is the only variable that strongly exceeds this threshold, whereas SP, SA, and other variables are just above the threshold. So the first thing we do is we remove the IC variable from the data set. And that's done in this line. Here I show you how to reproduce the result for the variance inflation factor for IC. So let's say we fit a model for IC explaining IC by all variables except for IC. So this you should be able to read by now. You have again, you select a subset, the data check to the columns, and the columns that you remove is IC. So we create a linear model again where we try to explain IC by all other variables. We see that 94% of the, even for the adjusted R squared, about 93% of all variation in the IC variable is explained by the other variable. So most of the information is somehow captured. And the variance inflation factor is calculated by 1 divided by 1 minus r squared. And it shows you that the result is 15.7. That's the same result, more or less, as we have been provided by the function here. Okay, we remove this variable and we keep all the other variables. We could recalculate the variance inflation factor again, for example, by typing with data and the new data set. This actually fails because this is just a data frame, of course. We would need to fit again the model like that. So let's quickly do this. Just for the purpose of demonstration. So we use the data in V, and we explain graphite species richness. Now we execute the variance inflation factor for this model again. And what we see is that by removing IC from the data set, we have got rid of the problem of collinearity, more or less. So there are still a couple of variables like SA or logarithmic depth that are relatively close to this variance inflation threshold provided in the literature, but we don't bother about this here. And I think unless you have several variables where this is the case, that they are close to this variance inflation threshold, we shouldn't worry too much. Okay, we have fitted here, we fit here the first model. With this model, I have to add that we also fit an interaction term. This is an interaction term between temperature and the logarithmic depth. So we account for the possibility that at low levels that the effect of one variable, or that the level of one variable affects the outcome for another variable. Let's say you have a low depth, that at low depths the temperature effect is much higher than at high depth. So this is just an assumption, has no scientific basis or something on which I make this. This is just for illustration purpose, that an interaction effect could be present and how to implement such an interaction effect in the linear model. What you see here is the interaction effect is included by the variable, then you have 2 points, and then you have the logarithmic depth. Run this model, and we see in the summary of this object. In the summary, we see the call, which function has been called. We see the residuals, or the median of the residuals. So that's the deviation from the ordinary least-square fit. And we obtain the coefficients for the different parts of this model, for the different variables that are included in the model. So on the one hand, you have the estimates for the different variables as well as for the intercept, and you obtain the standard error. The higher the standard error, for example for BT, this means that it's unlikely that it's, or the higher the standard error, the less certain this coefficient is, and we see this expressed in the p-value related to this coefficient. If the standard error is larger than the coefficient itself, that means that we have a variation that is so strong that the variable coefficient could always be 0 as well. And that is the test that is tested here with the t-value and then the related p-value, whether the regression coefficient for a variable is significantly different from 0. And this is not the case in this type of model for the several of the variables, as well as for the interaction term. Well, we know that such a model, this is the full model now. Now, for this model, we would be able to interpret the coefficients. That's what Harrell suggests, that only for the full model we obtain precise coefficients. But if we now remove variables from this model and have sequential testing, then we obtain some bias. We obtain too low confidence intervals or standard errors, and the p-values cannot be are biased low. So generally we should have about 10 to 20 variables per observation that we include in the model. We check this here. In our case, we ask how many rows this data set has. We see this about 140 observations, 135. We need a couple of degrees of freedom to estimate the intercept, to estimate other aspects of the model. So we have about 130 degrees of freedom left for the parameters. If we now say we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have about 13 degrees of freedom per variable. That's within the range where we can fit a linear regression model with reliable estimates. Doesn't mean that you can't fit it if you have a lower amount of data, but I discuss what you need to take care of in the lecture. We won't go into details here. The traditional modeling approach would be, or the traditional approaches we first discussed, one of the approaches is that you just construct a few alternative models. You choose the goodness of fit measure, and then you compare these different alternative models. However, I'm not an expert on marine ostracods, and the original study authors also did not do this, but they used modeling strategy, and is widely used. They use stepwise regression modeling. However, we are not starting with that here. What we are doing first is we compare all possible models. And again, I won't go into all theoretical problems of this approach. I just show you how to do this. Please recruit or refer to the lecture slides to know more about the appropriateness of this approach. So for multi-model interference, we use this library, MuMin, and to calculate all possible models, so that means you calculate all models where you have just one variable included, or combinations of two, and so on and so on. That's heaps of models, as you can already see. So this is easily done by the dredge function, where you just enter your model, and then we print the models. What we have here is we have different models. So we get a whole lot of output. For all the models, we have the log likelihood, the corrected AIC, the delta and IRC, so the difference in the corrected IRC, and the weight this model would obtain if we would use all of the models based on the AIC, on the corrected IIC, to be precise. So in the next step, we see that in the model selection table, latitude has been removed or is not included in models with a high AIC. Same holds for SA and in addition for the interaction term BT DPL. So we look at the AIC again. The AIC of these models is pretty close. There's a rule of thumb. Again, there are problems to this rule of thumb, but the rule of thumb says, well, within an AIC of 2, these models should be considered. If we do not just consider the best fit model, but we would follow a strategy to average the model, and I'm not going into details here, then we could do this using this rule of thumb that within a delta of 2 these models can be used. We use the function getModels that identifies all models that are a delta or a corrected IIC within the value of 2, maximum difference of 2 to the best fit model. And these models are selected. We call this. We see here the different types of models. It's 1, 2, 3, 4, 5 models have an AIC within a difference of 2, maximum difference of 2 to the best fit model. And now we average these 5 models. This is simply done by model.avg. What we see now is that we have here an averaged model from 5 different models, and we see which variables have been included in the different component models that were used for the model averaging. We see the coefficients of the model average coefficient, so that's the full average where every model has the same weight, and we see the conditional average if every model has the weight as defined by the different component models. We see this only varies, for example, for SA and for the intercept term. Yeah, so far we could now use this aggregated model, this average model, and check the fit of this, the R squared of this model. We do this with the predict function, so we have obtained the fitted model, fitted values, and we can calculate the residual and the total deviance for this model. We do this with the sum, so we sum up the squares between the observed rarefied species richness and the predicted species richness, and we take the sum of squares. And the same thing as we do, for the total variance, we calculate the species richness and subtract the mean of the species richness squared. What we then obtain, what we see is that we have about 50% of the variance explained, so the R square is 0.486. If we compare this R square to the models above, so let's look at the individual models. This is not necessarily the highest R square. For example, we had here slightly higher R square for this individual model that contained multiple variables. When we would fit this selected model here with the highest AIC, this might also have a different R squared. Keep in mind that the R-squared, of course, inflates for every additional variable that is included in the model. So this is not too surprising. The next technique we will look at is stepwise backward model selection using hypothesis testing on variables. And we've already discussed the problems of these techniques in the course, but I will show you how you do it in R, and we will compare it later on between different options and approaches that you can take to this. So let's start with the full model first. We have fitted this above, and we inspect this model and see that this interaction term is not significant. If you start removing variables, you would start removing non-significant interaction terms first. At least you would not remove variables like, let's say, bt in this case. You would not remove the main variable as long as the interaction term is still included in the model. So we remove the interaction term here. And that's easily done with the update function. You say update the model, comma for another argument, and it's tilde, dot, and then with the minus you indicate which variable should be removed. And this could be multiple variables. You could remove some, add others. You have several flexibilities with this update function. Let's see how this model looks like after we removed this interaction term. We see then now, except for latitude and SA, which is salinity, most of the or all of the variables are now significant. RC at least close to significance. So we remove latitude in the next step, and just quickly I remove that and call the summary function again, and we have another model to inspect. We see that RC is close to significant, SA shows no, is not much different from 0 according to this p-value. It's not significantly 0 different from 0, so we remove SA. That's the next step. Now we see that RC is more or less significant. All other variables are significant. Well, we could keep RC. We could also have kept SA and other variables if the aim is prediction, if we expect that the correlation structure between the variables is the same for new data sets. In this case, we want to know the most important variables, so we get rid of all variables that have not a high explanatory power. So we also remove RC. We do this, we call the summary function again, and we see that now all variables are statistically significantly different from 0, all individual terms of the model. Let's inspect the model. First, open the plot window, and we define here with mfrow that we have a 2-on-2 window, so we can see all 4 plots for regression diagnosis at the same time. We have discussed regression diagnosis in the lecture, so I'll only go quickly through that here. We see here the residual fitted values plot. Ideally, there shouldn't be any increase in variability, and it should be more or less a straight line. We see that this matches relatively well. There may be a slight increase in variability for higher fitted values, as we can see for the standardized or the square root of the standardized residual plots as well. Nevertheless, there's nothing to worry. If we look at the standardized residuals against the theoretical quantiles, we see that also fits the line here relatively smoothly. There's not much deviation, and if we look at the leverage points and their impact on the model, we have two leverage points, but these have not a high impact on the model, and we had a few points that deviate more strongly from the model are buffered more or less by other observations, so there's not much to worry here. So we've already closed this window. If you haven't closed it, you could close it with device off. I do this because we have now created a 2-on-2 window, so 4 plots in one window, and we don't want to have that in the next step. Now, many people say, well, this graphical inspection of models is difficult as a beginner. Are there any functions to help me? And one of these functions is the Q-reference function, because it shows you how residuals from a normal distribution would look like, and you can compare this to residuals from your model. So that's how the plot look like. That's the residuals of our model, and you compare these to the residuals that would be observed, or these are actually sampled from a normal distribution, and we see the shape of our data points, of our observations, is not much different to those sampled from a normal distribution. So we can conclude that our data, or we can conclude that it's not likely that we have to reject the hypothesis that our data comes from a normal distribution. Looks very, very similar to normally distributed data, not much deviation. If you have fitted a model, you can extract different information from this model. You have the coef function that gives you the coefficients for the regression equation. We have the confint function that gives you the confidence intervals for the regression coefficients. You could also manipulate, if you look into the function, which confidence intervals you want to obtain. You can receive the fitted models. These are the fitted data points, so without the error, and with the structure we can look at the different elements that you can extract from the fitted model. So you could also extract the R squared, the residuals, and so on. Now in this example we used the approach of manual model selection, backward selection. We started with the full model and removed variables. Now let's see what would happen. We compare this if we would rely on the partial f-test. So just compare the models. This would lead in this case to identical results. So we compare here the sum of squares, we compare the explained sum of squares between the two models and do an ANOVA. We see that there's no significant decline from a model with 1 or 2 sum from model 1 to model 2 when the interaction term has been removed. The same holds if we compare model 2 and model 3. The more parsimonious model has still no significantly lower sum of squares. And we do this for several other models. Again, no sign that we have a problem here. Model 1 and Model 4, Model 1 and Model 5. And we see that any of these comparisons is statistically significantly different. So that means we have nested models. We can use the partial f-test to see whether we have statistically significant difference in the variance that is explained by the model. And this is not the case here between any of the models. So what does this mean? If we have a similar explanatory power, so we cannot reject the hypothesis that the explanatory power differs between the models, then we should of course use the model that has the lower amount of variables. Because if you can explain something with fewer variables, why should you use more variables? Another approach or another goodness of fit measure, other than hypothesis testing that we have discussed in the lecture, are information criteria. And we have on the one hand, we have the archaic information criterion. We had discussed the Bayesian information criterion, and finally we have the corrected IIC for lower sample sizes. So we calculate all of them here and see what they would suggest for identification of the best fit model. So let's fit the AIC first, and we see we just obtain the result for the AIC. Note that the smaller the better is the model fit based on this information criterion. We see here that the AIC would actually suggest that model 4 is the most parsimonious or the most appropriate model. If we use instead the BIC, just fit all this, then we see we have for the BIC we have a constant decline from 780 to 767. So we would also, this would also suggest that we keep the model 5. But note, I mean, in this case, if we would do this manually, we would remove another variable and check whether the BIC would lead decline even more if another variable is removed from the model. So finally, I just show this here in this case. It's not really necessary for the AIC. We have the corrected IIC. We see that leads to the same results here. I'll also show you in the script how you can calculate the corrected AIC yourself if you don't want to load a new package. It's just dependent on the number of coefficients in the model, so that's k, and you have the number of data points. Then you have the formula here. You have displayed the formula on the slides for the lecture, and you obtain the same result as for the one that is calculated automatically when running the corrected IIC function AIC minus C. So that was manual model building. In the next step, we look at automatic model building. I have put several statements of caution on the lecture slides. I'm not repeating them here. Should be aware that just running automatic model building is no solution to scientific problems. You need to know what you are doing, why you are including variables, and then you can make inference. The computer can't decide for you and just tell you which variables are most important, and would also select spurious ones. So what happens if you run such a model? Or let's first again go back to how you set up such a model. First of all, you fit a null model. That's the model that you would say, well, that is the smallest reasonable model that we could assume. In this case, this is a model without any variables. It would contain only the mean that is fitted by the response variable tilde 1. You could also say, well, the null model is a model that contains at least 1 or 2 specific variables. I don't want to have any model with less than these variables because we have solid evidence that these variables are of high importance. Then you have the step function. The step function does the stepwise modeling. You have entered the model that you start with, then you say which direction you want to run the stepwise regression, and you have the scope. The scope here is the upper model, the most upper model that you have to provide. You have to provide this mainly when you do forward and backward entering of variables. Just do this to simplify the code here for the forward modeling. So here we say, well, the upper limit is the model 1, shouldn't include more variables that is contained in model 1, and the lowest model, so that is the model, well, that is the upper end, is the null model. Note that we use the BIC here, so we want to be more restrictive because we want to find the most parsimonious model. So that's k equal log n. If you leave the default, which is k equals 2, then you would use the AIC. And you see the algorithm in R calculates for the initial model the AIC, and then it checks how the AIC would change if nothing would be done or if a variable would be removed, and compares this AIC to the initial AIC. And as long as this, as one of the AICs for removing one of the variables or terms, better one of the terms including interaction terms, leads to a lower AIC, this is executed. And it just focuses, of course, not on any scientific meaning of the variables. It just selects that one that has the lowest AIC. So we see this is done again and again. First it removes ARC, fits the model again, now without RC, then checks what happens if another term is excluded from the model, and fits the model again after excluding the next term, which is latitude. And this goes on and on until we arrive at the final model that only contains 5 variables. So this is the model where longitude SP, P, BT, and dp log are still contained. And we get the regression coefficients here. You could also run step function with forward modeling. And what is interesting here, we start with the null model, and the first variable that is included is SA. So that means that would be the most single most important variable if we just include one variable according to this procedure. And we end up with a different model. It is the same model as the one above, but also including SA. So it contains one variable more. So that should cast some doubt on these procedures as well, because if you change a different direction of the procedure, you obtain a different model, and the variable that is supposed to be one of the most important alone, SA, is not included in the backward model. We can't say which one is correct or incorrect. As you know, SA is highly correlated with dp log, and we would need salinity and the logarithmic depth, which makes sense, and we would need more information on the system that we are looking at to decide, well, is this a correlation where actually only salinity is physiologically effective and the logarithm of the depth is just a spurious correlation that is not that important for the model and could be removed, or does depth, the logarithm of depth, have an individual important explanatory power? For example, there is less light and less food. That may be another explanation. Well, we don't know, why we don't speculate, but this shows if you have such results, don't just let the computer decide what is the best model. We discussed in a lecture that there are several problems related to this approach. One problem is that we have regression coefficients that are biased high, and one possibility to correct for this is to run post-selection shrinkage that may yield to more accurate regression coefficients. For this, we use the library shrink, and we have two options. We could either shrink the whole model with all variables the same, where the same factor is applied to each variable, or we can have parameter-wise shrinkage. And in some comparison paper, they found that this parameter-wise shrinkage is more accurate. Anyway, before we can shrink, we need to remove some variables from the model, and so, or we need to set up a new model. We set up model 5 as shrinkage, and one important aspect, we need to provide some matrices that are important, some elements, some information for this shrinkage function that is not provided by default by the LM function. So we fit the LM function again with x equal true and y equal true. So if you run the summary function of that on this, you would obtain the same result. And then we can run the shrinkage function. That's just shrink the model and the type of shrinkage that you want to use. So we shrink the regression coefficients, and we see that there's a shrinkage factor that's 0.911, so approximately 10% of the regression coefficients are shrunk. And if you compare this to the original regression results, so type QF mod 5, we see that the regression results in the upper row here are approximately 10% lower than those of the model 5 that has not been shrunk. To reproduce the results, you see that is how this is calculated. You just take the shrinkage factor, multiply it with the regression coefficients. Now we conduct parameter-wise shrinkage. So each parameter is shrunk individually based on its importance in the model. So refer to this publication for more information. And what we see here now, if we compare this to the original model, then we see that there is a different amount of shrinkage. For example, SP is much more shrunk in this model compared to BT, that is not as much shrunk. And longitude is also shrunk to a stronger extent compared, or is not, to a similar extent. That's about 30%. Okay, here's about a little bit more for P. So we see they are different, and at least it differs to the extent to which it has been shrunk. So why do we do this? With these shrunken regression coefficients, we would expect that we have a higher explanatory power or higher predictive power for new data sets. Another approach to deal with the problems of stepwise model selection is to put this whole stepwise model selection process into a bootstrap algorithm. That means we draw several random data sets from our initial data sets and we check whether these sample data that has the same characteristics as the initial data, whether when we have these different random data sets, whether the bootstrap data, overall data sets yields to similar conclusions regarding which variables are important and so on. For this we require the library bootstrap AIC, and first we construct a new data frame because we need the response variable and the explanatory variable in one data frame. Later on you will see, if we use the LASSO algorithm, that we also need to set up a new model. So these models always contain the same variables, so explanatory and the response variables, but the R function that uses these input data requires us to provide different formats of the objects, different classes of the objects. So that is the whole reason why we do this. And you have to be very careful for other R functions to make sure that you always provide the correct type of object. So it's not about the content itself in terms of scientific content, so we always have the same variables, but it's different classes that you need to plug into the functions. That's just the way the functions have been designed. So here we use the setSeed function. The setSeed function makes sure that the results are always the same. As you know, a computer can't be really random in the sense that it's completely unpredictable. It starts with some random number generator, and which random number generator is used, or how these random numbers are generated, can be controlled by setting this seed. So we make sure that on all computers and for everybody running the script, we obtain the same results because the same random numbers are used. Now we run the bootstrap AIC function. So it has as input the model, the data set that contains all explanatory and predictor variables, the term that tells whether the BIC or AIC should be used in model selection, and the direction. This takes a little bit for this number of variables. And what is the output here? We see the call to the function. We see that 100 bootstrap samples have been used, and the penalty term, this is log n, that has been used in this modeling. And what we see is how often particular variables have been included in the model. And this is a little bit sobering result, because we see that most of the time none of the variables has been selected. We can't really decide based on these results. Here we see the consistency in the signs of the variables if they had been included. You see that only latitude, P, and SP have always a negative sign. That means, depending on the model specification, a variable can have a positive or a negative effect on the response, which is a little bit strange, or it should ring a bell for caution in interpreting that, because if the same variable can have a positive and a negative relationship with the response, well, that is not ontologically possible. So in reality, it can only have a positive or a negative relationship. Then we see the statistical significance for the variables when included in the model, and the coefficients for the final model, or for the variables for the model that contains for the original data set, the stepwise model path, and if we just use the step-IIC function as we have done above. So for the BIC, it's a very, very restrictive model. If we just sample random data from our initial data, should cast some doubt at least in us. If we use the AIC instead, takes a little bit. So we then see that we select covariates much more often. We never end up with a null model for this bootstrapping, and we see that indeed the interaction term in this case is selected, one of the least variables selected, the interaction term. Nevertheless, there is no clear spread, so we have more or less a continuous number of times, continuous distribution of the number of times how often a variable is selected. There are no clear gaps where you could say, well, this model or this variable could surely be excluded. Or actually, I was wrong here, is 17% of the times we actually yield to a null model. Here we see the signs, the coefficient signs. Again, it's problematic if you have 50% of the time a positive and a negative sign. That should at least cast some doubt on the power. And here the statistical significance of the variables when they were included in the model. Overall, we know that Austin, and we mentioned this in the lecture already, that Austin 2008 cautioned against the use of bootstrapping to fix problems of step-size selection. And C. Herald 2015 as well for related problems. We don't look into cross-validation, how this is done in R for the whole modeling procedure, but you can follow this link here. Another problem of hypothesis testing is the sequential testing. This is fixed in the package selective inference. Again, we have to fix the model here again. So we call the library selective inference. And this function requires, again, a different format of our data, here requiring us to provide the class matrix with the predictors and the class and the vector of the response variable. So we see even the position inside the function is changed here. First explanatory, then response variable. We can easily do that using the as matrix function that converts our data into a matrix. And then we fit this function. What it shows us is how the regression coefficients change over the different steps in normal stepwise model building. Now we want to draw some inference for the model and correct for hypothesis testing, for multiple times hypothesis testing, and we obtain this output. So what we see here is what we obtain is the estimated stopping point from the forward stop rule. That would be 0.5, but we see also sequential testing results for entering additional variables in the model, and we see that only for variable 8, 3 and 2 we obtain statistical significance. We can extract coefficients from such a model. For example, here we have for variable 2, 3, 5, 7 and 8. These would be the regression coefficients. We want to know what is the name of these variables? Actually, we can just call our initial data set. We see RC would be 0, BT -1, SA, and so on. We also see here, this is the position of the variable in column-wise. And we see here that the third variable, SA, again pops up as the most important, followed by BT, and followed by the depth logarithm. So if we would just take this sequential p-values, we could also argue that only 3 variables, namely dp log, bt, and sa, are relevant in our case. Yeah, so much about stepwise model building. As you know from the lecture, if you have to use stepwise model building, then rather use backward stepwise model building and use in conjunction with shrinkage of coefficients. At least this is what Harold suggests. I would actually favor a different approach, that is the LASSO approach, and I show you how you use this approach now. First have to call the function glmnet. So the LASSO actually includes another penalty parameter on the sum of the regression coefficients. That means there is a force to not overfit the model and to have low regression coefficients. So we have shrinkage of regression coefficients during model fitting. Model fitting is again done here really easily. It follows the same syntax. So first we provide a matrix of the different variables that are explanatory, and then we have the response variable. Fit the LASSO, make sure that no previous device is open, and then we set new parameters for the new device. Plot this, and what we see here is that is the penalty term. So we see in the small numbers, we see the variables. 8 is dp log, 2 is bt, and 4 is sp. So we see that's a slight difference, but sa is also contained in model. That's 3. That's a slight difference here compared to the other models. So the larger the impact, the L1 norm, the L1 norm is actually the sum of the betas. We see that the smaller the sum of all betas, this leads to removal of variables. What we see here is the number of variables in the model at different sums of the betas, of the regression coefficients. We can also display this in a different way. This is the lambda. So the lower the lambda, the less is the penalty on the model. We see the higher the lambda gets, the lower the coefficients of the variables become, unless in the end there's only one variable left. We can again see that 8, 2, and 4, these variables, and maybe 3, have a relatively high importance. Finally, we can plot coefficients against the fraction of deviance explained. Deviance is just the generalization of explained variance for generalized linear models and so on. can extract the coefficients. What we can learn here is this is actually the coefficients of the different models for different lambdas, and we see for the highest penalty that we have only a model with an intercept and then additional variables are added. We see here that BT, SA, P and dP log are the most important variables that coincides with our previous observation using other techniques. We can obtain the optimal lambda based on cross-validation, so we remove data and fit the model again and again and look at the cross-validation error. We provide here again the variables in matrix form and the response. We set the seed again to ascertain that everybody who runs this obtains the same result. And then we plot the fit. And in this case, we have on the one hand, we have the lowest lambda that is indicated here, and we have the lambda where the standard error is just that is still within one standard error. Following the rationale that when it's still within one standard error, it's not very different in the mean squared error, although it's a little bit higher than the original model, and we fit this again. And we could use this model to be more parsimonious. However, we see that the lowest lambdas actually and the border here, and we fit again using lower lambdas. So that means we want to have more observations here, because it could be that the mean squared error drops much more if we had additional sample points or additional lambdas that we use in the modeling to the left. So we take a wider range of lambdas here, and now we see we have lots of lambdas left to the optimal lambda. The optimal lambda is approximately at a log lambda of -4 point something, and we have the optimal minimum within one standard error, still overlapping with the minimum model. We have here around -1 or something like that. And this above these numbers give us the number of variables included in the model. So if we go for the minimum lambda here, we obtain the number of the lambda, the penalty term for the minimum cross-validation error, and for the cross-validation error where the model is still, where the cross-validation error is still within one standard error. We extract these coefficients for these models. We see it on the one hand, we have all variables included. On the other hand, for the one standard error model, we have latitude excluded. So what we can conclude here is that, well, generally the LASSO suggests that the model, depending whether we use this one standard error model, which I would suggest, that we have the most parsimonious model if we only exclude latitude. We compare our regression coefficients. So we extract, so we construct a new data frame with our initial coefficients from ordinary stepwise selection. We take the one from model 3, where we still have SA included and RC, and we compare this to the coefficients that we have just fitted. We provide names to the columns in our data frame, and then we plot this, and what we see is that the LASSO shrinkage leads to shrinkage in all parameters, all regression coefficients, except for SA, that is considered as the most important variable. Yeah, that's it for the lasso. Finally, I show you if you had used a technique where you don't have done cross-validation, then you can validate the model in the end using k-fold cross-validation. You need this type of code for that. And so we calculate the validation for model 4 and 5. What we see is that the original R-square was 0.49, and in cross-validation this value drops to 0.41. So cross-validation means that you remove parts of the data and try to predict this part of the data from the remaining data, just to remind you. And for both model 4 and 5, we have a drop of 6 to 7% reduction. Of course, that would also depend on, that is how the data are split up. We can set seed here as well to have reproducible results. So if I fit this again, that was an error, set seed, fit this model again. That does actually not work for this function, I just realized. Okay, that just means we have to go with that. So the shrinkage is about 4 to 6 points depending on the algorithm, depending on the split of samples. So I put here roughly 5 and roughly 6. Notice that generally with cross-validation we underestimate the true test error because we use data that has the same characteristics as the data that has been used for fitting. And finally, for relative importance of the variables, we use the RelaImpo package. This function is used for model 5. We use different variable importance measures, and again this is only relevant if we don't have variable importance measures provided for our data set. It is always here in terms of R². Please check yourself the help to this function to find out what these different variable importance measures mean. We have discussed them in the lecture, and you obtain this plot that shows you the variable that's important. That's for hierarchical partitioning. It's probably the method that is most reliable, especially if you look at the R². And then we see here that BT, P, and the logarithm of depth are the most important variables. And that matches reasonably well with the results that we obtained for the LASSO. Another way of displaying this, and we do this here for model 3, is the function, the library higher part. It contains a function called here part that we execute. So it has more or less a similar. It has a little bit different syntax. So we fit the response variable and then the explanatory variables, and then which goodness of fit measure should be used. Actually, different goodness of fit measures can be used for this function. And the result, if we have the model that would be the optimal LASSO model, and we see that we come here to based on R² to the same conclusion that BT, DP log, P, and SA are the most important variables in this model, and we can conclude based on now our scientific roadway that these 4 variables are most important, which was our initial question. With that, we are at the end of this screencast. I've showed you many different techniques to implement multiple regression analysis, and now it's your turn. Please go through exercise 4 and fit a linear regression model yourself. What you should do is, of course, to look at the data before, whether you have Co Linearity that is problematic, whether you have differences in the distribution of the various, strong differences at least, and whether you have and then build the models, use manual model building, use automatic backward model selection with post-selection shrinkage, and then compare this to the LASSO results, to the LASSO shrinkage. That's all. Thank you very much for listening, and see you in the next video.